And I'm going to state this in a very simple way. So there is some constant bigger than 1 such that for every elliptic curve over Q, we have that the absolute value of the minimal discriminant is bounded by the conductor of E to that power. Okay? That's the motivation. And when you apply this to Frey curves, you end up with the following conjecture, which I'm not going to state in the strongest form, but rather the form that follows right out of this. And I'm going to call this ABC, although there are other versions that you may find under this name. So ABC conjecture is that there is certain constant such that for every triple A, B, and C, let me say of positive integers, they are coprime with A plus B equal to C. We have that A times B times C is less than the radical of A times B times C to the power kappa, where the radical of an integer is just the product of the different primes dividing the integer without repetitions, okay? Good. Now this is of course open, and we don't know very much about this. All right, so let me just go straight to the theorem. Okay, this is using too much space here. Okay. So the theorem, one of the theorems I want to discuss today is the following. So let epsilon be positive. Then for all A, B, C as above, coprime with A plus B equal to C, we have that the product for P dividing A, B, C of the p-adic valuations of A, B, C is less than the radical of A, B, C to the power 8 by 3 plus epsilon. So this notation is just standard Vinogradov notation, meaning that there is some constant that depends on epsilon. In case you're wondering, the constant is effective, although I didn't compute it, but it is effective. And if you don't like the epsilon, you can forget about the epsilon and think about a radical cube if you want, okay? All right, so that's the theorem, and certainly if you compare these things, this seems much weaker than the ABC conjecture, and in fact it is much weaker. But I'd like to remind you what else we know, which is actually not very much. So what other kind of unconditional results are out there? Well, compare some comparison. There is linear forms in logarithms that give you bounds of the following sort. The maximum for P dividing A, B, C of the p-adic valuations is less than the radical of A, B, C to the power alpha plus epsilon, where I need to give some credit here. So with alpha equal 15 due to Stewart and Teichmann, and this is in 86, and then alpha equal 2 by 3, this is Stewart and Yu, in 91. And then alpha was lowered to 1/3, Stewart and you again. And this is in 2001, and that's where we are now. So previous results using transcendental number theory, they give you bounds. There are a power of the radical, they are polynomial on the radical, but for the maximum of the p-adic valuations. And that's what we knew. What I'm saying now is that you can give such a polynomial bound, with a different exponent, of course, but for the product of all these valuations. And that's actually a crucial difference for some applications. First, I'm not bounding a priori how many prime divisors you have. So if you just want to deduce something like that from here, a priori it just doesn't work, because these contributions pile up, and this implicit constant shows up in the form of exponential of some number of prime factors, and in addition you have this radical to the power number of prime factors, and that's not necessarily polynomial on the radical. But I mean, that's arguing by saying what we don't see how to do, but let me be more concrete here. Here's a very concrete application concerning Tamagawa factors, or the so-called Fuchs factors. All right, so let epsilon be positive. Then for every E over Q semi-stable, and actually this is not really necessary. You can get a result in more generality, but I want to somehow improve the exponent in the inequality, and that helps, okay? We have that the Tamagawa number of E, which is defined as product of the local Fuchs factors. This is polynomial on the conductor. And I work out the exponent 9/2 plus epsilon. All right. So there is this application. Now, if you're not familiar with this, this is the Fuchs factor showing up in the conjecture, in the BSD conjecture, in the special value formula, okay? And there is a standard conjecture. Let me just mention here, remark. There is the following conjecture that says that tam of E should be bounded by the conductor to the power epsilon. That's the conjecture. We're nowhere close to prove this. This implies many things. In particular, it implies a sub-exponential version of the ABC conjecture, which we don't have. And this has been discussed in the literature, so I also need to mention some names here. There is a strategy for this due to the Vega, and independently by Hindry. And the strategy is a very simple observation, but nonetheless gives you a feeling of what's actually going on here. So they observe that tam of E is less than or equal to, you need to work out what are these local factors, but this is less than or equal to the number of divisors, sigma 0 or D, depending on your notation, of the minimal discriminant squared, okay? And well, this is the discriminant of the elliptic curve. It's some positive integer. It's absolute value. So the best we can say at this point is that this is less than exponential of some constant times log delta divided by log delta, okay? That's a general estimate for the number of divisors. And if you want to prove this conjecture going along these lines, what do you need? You will need that log delta is less than any positive constant times okay. I guess, yeah. Good, okay, this is complicated to manipulate. Okay, good. So you will need what you will need is that log delta is little o of log n times log n. Okay, that will imply that conjecture on the size of Tamagawa factors. We don't have it, and in fact, what we know is that log delta is bounded by n to some power. I don't want to be precise on the exponent, okay? Depending on what are you assuming about your elliptic curve. But this is exponential. Now, if you want to prove my theorem along these lines, what you will need, so our result will need log delta bounded by constant times log n times log n. Okay? So that strategy will not give you the result, at least not with the technology we have today. Okay? So, right. So the product of local, the product of evaluations, this theorem I have here, actually is a particular case of a more general theorem I prove, applied to the case of Frey curves. And that more general theorem is what gives you the bound on Tamagawa numbers. And it deals directly with this product of local contributions. It doesn't reduce to number of divisors or to estimates on, along the lines of the Weger-Hindley strategy. So that's what I mean when I say that for some applications, you really need to work with the product of the local contributions rather than each valuation at the same time. Is independently, okay? Good, so that's with the results. Now, I'd like to mention something else you can do with the techniques I want to discuss today. Here's another theorem. So let F be a totally real number field with degree F over Q n. So this is my definition of little n. Now, given E over F semi-stable elliptic curve, which is modular with modular parametrization phi from x to E, and x here is a Shimura curve over F, we have that the Faltings height of E is less than 1 over 2, the logarithm of the degree of phi plus certain number that only depends on the degree, otherwise it's independent of the particular number field, times logarithm of the norm of the conductor of the conductor ideal of E plus logarithm of the absolute value of the discriminant of F. Okay. Now, if you're familiar with the literature on the ABC conjecture, you will recognize some similarity with the usual modular approach to the ABC conjecture over Q. So when you work over Q, you have these modular parametrizations coming from modular curves, and we know that the Faltings height is bounded logarithmically on the degree of an optimal modular parametrization. And the hope is that you can control those degrees and prove the ABC conjecture in that way. So that's what's called the modular approach, the classical modular approach. What I'm saying is that something like that also works for modular elliptic curves over totally real number fields. And in that case, of course, you have more freedom to choose the number field. And it makes sense to ask, okay, how does it compare to Vojta's conjectures? Yes?
So you don't assume this parameterization to be optimal in some way?
Well, it's an upper bound, so it doesn't matter.
Okay.
Right? If you want to use the optimal one, you get a better result, but it's an upper bound. If it were a lower bound, of course, you need to be really careful which one you're using. Okay. So I was saying that now here you have the freedom to choose your number field, and it makes sense to compare this with other conjectures, for instance, conjectures of Vojta that concern extensions of the ABC conjecture for algebraic numbers of bounded degree. And you like to see dependence on the number field, but not in just any random way. You like to see this polynomially on the discriminant of the number field. And that's precisely what shows up in this inequality. Okay? So in that sense, this is pointing in the direction that the dependence on the number field at least is correct. Okay? Of course, that leaves with the question how you control this degree. Now, I also give estimates for this degree using congruences, but let me not discuss that today. All right, let me move this up. So you can move two of them simultaneously. Okay. Okay, so that's with the results I want to mention. And now let me just dive into the strategy. So maybe I should start by saying what I'm not doing. Okay, so here's what I'm not doing. The classical modular approach. So let me just write down something that I mentioned some moments ago. If you start with some elliptic curve E over Q, then you have a modular parameterization coming from a modular curve x0n to E, and let me assume that this is optimal. But if I'm going to assume that this is optimal, maybe I should be more careful here. And it's actually not necessarily going to E. It's going to some elliptic curve which is isogynous to E. But it's not a serious issue because this degree is at most 163 by Mazur. Okay? So it's not a very serious issue. But now this allows me to define a number. Delta is going to be the degree of phi, and this is an isogeny, is a number attached to the isogeny class, of course. And all right. Now I also have a Manin constant that shows up in the following way. You take a phi, pull back an Heron differential of A. This is going to be a certain multiple of a normalized modular form. So 2 pi I C E F Z dz. I'm also composing with the standard uniformization of the modular curve, but locally it looks like this. And this guy is what's called the Manin constant. And this F is chosen so that the Fourier expansion starts with 1, okay? It's a normalized one. All right, so what happens here is that a very elementary computation gives you that the logarithm of this degree is equal to twice logarithm of 2 pi Manin constant, which I'm assuming is positive. I have some freedom here, plus or minus 1, so I can assume this CE is positive, plus twice logarithm of the non-normalized Petersson norm, okay? So this F has weight 2, so this is the Petersson norm in that case, plus twice the Faltings height of A, which essentially is the same thing as the Faltings height of E because the degree of the isogeny is bounded. And well, so you end up with this expression just by computing volumes and pulling back. And the important thing is that the Manin constant is known to be an integer. So you have a priori a lower bound for this term. Now, F is Fourier expansion normalized, so you have a priori a lower bound for this term also. You do the math and you end up with the following inequality. That, which one is it? Okay, 2 height of E, not A, is less than logarithm of this degree plus 18, okay? I work out the numbers, but the 18 in particular is not really important. All right, and that's the modular, this is the modular approach, the classical one, to the ABC conjecture. Because now the problem is reduced to showing that this modular degree, the degree of this parametrization, can be bounded polynomially on the conductor of E. You can do that, then you get a logarithmic bound for the Faltin's height, and that implies Szpiro's conjecture, which implies a version of the ABC conjecture, okay? And this has been around since the 80s. So this is what I'm not doing, okay? So let me tell you now what I'm actually doing. All right, so now I want to say a couple of things about Shimura curves. Shimura curves. So, all right, so N, capital N is going to be the conductor of E, which by results of Carayol agrees with the level of this parametrization, okay? So that's my notation. Now let me take a factorization N equals B times M. Admissible. Admissible. Now this means that mu of D is equal to 1, and that D is co-prime to M. Okay, that's what admissible means. So this is the product of an even number of different prime factors. It's square free and even number of prime factors. All right, so take a factorization of this sort, and all right, so attached to this factorization, you also have a certain curve, the Shimura curve, attached to the quaternion algebra of discriminant D with the level structure gamma 0 dm, coming from an Eichler order. And this guy has a Jacobian, which I'm writing J0 dm. Everything here is defined over Q. And by the Jacob-Langlands transfer, so one has the Jacob-Langlands transfer, which will tell you that you have a certain quotient here coming from the Jacobian. And I'm going to assume that this is optimal. So I have here an ADM, which is isogenous to the original curve E. And now I'd like to talk about modular parametrization coming from the Shimura curve, but I can't a priori. The reason is that, as we all know, Shimura curves are really pointless. So they don't have real points. So in particular, there is no clear way how to map the Shimura curve to the Jacobian. You need to do something, okay? And you need to choose this map in a way that's very economical in terms of degrees. So that can be done. Not in a unique way, but it can be done. So you end up with certain phi dm coming from x0 dm, and since this is not unique, there is no harm in composing with the isogeny, and you land in E, okay? All right, so what does it mean to be economical in terms of degrees? So there is a candidate for degree here, right? And this candidate is the following number, delta dm, which you define as the composition q dm composed with q dm dual. So everything here is principally polarized. They are Jacobians and elliptic curves. So you get this integer. And it turns out that this is a good candidate for the degree of the map. And in fact, there is such a modular parameterization phi dm, which phi I'm using, yeah, phi dm, with delta dm approximately equal to the degree of this thing. Okay, so they are essentially the same thing up to an epsilon in the exponent. Okay, good, good. So that's a good start. Okay. Now what? Now, all right, first thing you try to do is to adapt the modular approach to the Shimura curve case, cross fingers, and hope that you will get better bounds. Actually, that works, okay? But I don't want to talk about that today. Instead, here's something else you can try to do. So compare delta and these several delta VMs. All right. So by comparison, I mean just look at the quotient of this, okay, at the fraction, and ask yourself, what is that fraction? So how much does the degree change with my choice of factorization? Now, this is a well-defined question because this number is canonical. I can approximate it with a degree, but this number itself is canonical. All right, so here's the theorem. And this is Ribet and Takahashi plus some work dealing with reducible Galois representations that actually show up in the analysis, because you know that Frey curves, they do have two torsion, rational two torsion. So you will have reducible Galois representations, and you really want to control all of those. And the result here is that there is certain gamma that depends on everything inside. Such that delta by delta Vm is equal to gamma times the product by of P dividing D of the p-adic valuation of delta. Okay, that's not very interesting. I think everyone here can prove this. But the interesting part is, what is this gamma, right? So take this as definition of gamma. Okay, and the height, the logarithmic height of gamma, is bounded by log n divided by log n with an implicit constant that depends on s. And here, from now on, s contains, is a finite set of primes that contains places of additive reduction. Okay? So you fix a set of primes and work with the curves that have additive reduction contained in there. So for instance, if you care about Frey curves, you'd like to take S equal the set of primes containing just 2. Okay? All right, so what this is saying is that up to a factor that for all practical purposes I can forget about, this fraction is equal to a product of valuations, which is the kind of object I want to consider. Now, the whole point of the approach I want to explain is that although we have terrible control on these degrees, as of today we can just control them exponentially on the level, the variation of the degrees is way simpler to control. I mean, it's still hard, but actually something one can do. And the variation of the degrees, one can bound it polynomially, not exponentially. The question is that good for anything? And the answer is yes, because this variation of degrees is telling you information about the minimal discriminant, which, as I explained at the beginning of the lecture, is something that gives you results that we didn't have access before. Okay. All right. But this is like step 0. We actually have to work here in controlling that fraction. So how you show that the fraction of 2 integers is not too big? Well, you show that one can show that the numerator is not too big and the denominator is not too small. Sounds easy. The problem is that my claim is that that fraction is at most polynomial on the level. And for that matter, you will have to show that the numerator is polynomial and the denominator is not too big. Sorry, it's not too small. But if you were able to show that the degree in the numerator is polynomial, then you prove the ABC conjecture. So that's not the way to go. Okay, you have to do something else. All right. So sketch. Okay, let me give an idea of what's going on here. So we'll consider a simpler theorem that I can somehow outline. There is some exponent such that for every elliptic curve E over Q, semi-stable away from a fixed set S, okay, set S of primes, we have that the product for P dividing the, well, a P prime of bad reduction VP delta is less than the radical, the conductor to the power kappa, and maybe an implicit constant if you want to be careful about the exponent. Now, this is weaker compared with the theorems I mentioned at the beginning of the lecture. So I'm not claiming this implies those. You have to really work harder to get a good exponent here. I just want to explain this to give a feeling of how the proof works, okay? Okay, good. So a polynomial bound for the product of the valuations. That's what I want to explain. All right, so how it works. So there is a reason why I mentioned this classical modular approach. Although I'm not using it, there is an equation in that computation that's being used. So do we still have it here? Yes, it's right there. So that equation expressing the degree in terms of a Peterson norm and a height. Okay, that's actually something that one can make use of. So recall that we have this log of the classical modular degree is equal to twice log of the Manin constant plus twice log of a Peterson norm, more precisely the one of the modular form which is Fourier normalized, plus twice the height of E. Now this is not quite looking like the thing I wrote there, so I need to add a bounded error term, okay? This bounded error term absorbs the contribution of the isogeny and absorbs the logarithm of 2 pi. Okay, fine. So I have this expression coming from the classical modular approach. Now, it turns out that this is asymptotic to twice log CE plus log n plus twice height of E. So of course the only change is there. And the reason, well, this is classical. This is coming from the analytic number theory associated to the symmetric square L function, okay? So that's something that actually we know, how to deal with Peterson norm of a Fourier expansion normalized. So maybe I should clarify that point. This is coming from a Fourier expansion normalization. All right, so that's an expression for the degree of the classical modular parametrization, which is the thing that appears in the numerator in that extended Ribet-Takahashi formula. And now the denominator should look like this, more or less, right? Which will be great, because in that case, when you take the difference of the logarithms, you will be able to cancel this height. And the height has a huge contribution. So that should help, okay? Now, there is an issue with this. It's a very serious issue, actually. So logarithm of the degree of this phi dm, which, as we agreed, this thing is more or less the same as delta dm, okay? So I think I mentioned that before. Yeah, it's there, okay? So it's more or less the same. But this is the geometric realization of the other number. So this is equal to twice log Peterson norm of what I'm going to call FDM. And this is a quaternionic modular form, actually, plus height of E. sorry, there is a 2 here, twice the Faltings height of E, where when you pull back phi dm, okay, you pull back a net-on differential on E, you get, by definition, this f dm z dz. So that's my definition of FDM. It's just whatever you get as a pullback. Now, this is somehow different to the classical case, because in the classical case, I said I want to deal with the modular form, which is Fourier expansion normalized. And that has a price, and the price is to introduce the Manin constant, right? Okay, in this case, I don't have a Fourier expansion. These Shimura curves come out of compact quotients in general, when d is larger than 1. So there is no CASP, there is no Fourier expansion, and there is no analytic way to normalize this thing which is compatible with arithmetic, okay? So if I want this formula to be correct, I have one and only one choice, which is just take whatever the pullback is giving you. The problem with this is that this is an arithmetic normalization, and we don't really have control on this Peterson norm, okay? We're just giving names to it. It's not really helping. Okay, in any case, and perhaps I can use this. Okay, in any case, that gives something. Oh, here, yeah. That gives that the logarithm of the product for P dividing D of BP delta is asymptotic to twice logarithm of the Manin constant plus logarithm of n minus twice logarithm of that Peterson norm of the quaternionic modular form. Okay, oops, yeah, we get this. Now, why? Because you use this modified Ribet-Takahashi, you take logarithms, and you get cancellation of the contribution of the Faltings height. That's what's going on here, okay? If you're familiar with this topic, you may be worried about why I keep writing the Manin constant. Isn't that thing supposed to be small? Yes, conjecturally, okay? Conjecturally small. In the semi-stable case, we know that it's 1 or 2, or if you take into account also some recent work by Chesnavicius, it's actually 1. The problem is that I'm not working on the semi-stable case, because actually for applications on the ABC conjecture, I need to allow additive reduction. And at the nastiest prime, which is p equals 2. All right, so that's an issue. But all right, so that means we have to prove something here. And here is a theorem. Is that the Manin constant, if you fix a set of primes containing the primes of additive reduction and you vary your elliptic curve, allowing additive reduction there, then the Manin constant is bounded, in fact. Okay? And I'm saying nothing about this proof because it's some technical arithmetic geometric computation on certain Stucky integral models of modular curves and using theory of Eisenstein models, but let me just say that we have this bound, okay? All right, so that means that we only have to show that this f dm not too small. That's what we need to do. So we need to show that if this Peterson norm is small, it's not too small. At worst, it's reciprocal of a power of the level. That's acceptable. That will still give me a polynomial bound of the sort I want. But it wouldn't be acceptable that this is exponentially small. All right? And the issue, of course, is the lack of Fourier expansion, how we deal with that thing. And in fact, this is actually the complicated part of the argument. So, all right. So I can write here a little setup. So instead of dealing with this particular case, I prove something more general that in particular captures this situation. So let me start with, okay, so some notation. So we have x0 dm, which is a coarse moduli space for elliptic surfaces with quaternionic multiplication, and this thing is defined over Q. But actually, you can extend the modular problem and get an integral model that solves that coarsely, and that gives you the x0 dm. Okay, and so this is very similar to the theory of the Lin, Rappaport, and Katzmeiser, except that there is some contribution at primes dividing d that comes from work of other people. But all right, so this thing is over z. Okay, this is flat over z. In fact, projective when d is larger than, well, in the other case also. So it's flat and projected. And all right. Now, I'd like to use this integral model to give a certain lattice, a certain integral structure of modular forms. So I'm going to define E dm to be H0 of the smooth, on the smooth locus, okay, of this structure map of relative differentials. Okay? And that thing is going to give me a lattice, not full rank, but it's an integral, let me just say integral structure on the space of way 2 modular forms in the quaternionic case. All right. So in the classical modular case, what is the lattice? What is the integral structure one usually considers? The one coming from Fourier expansion. Okay? But here I don't have Fourier expansion. So if I need a substitute, this is a very reasonable substitute. Okay? Now I restrict my attention to the smooth locus so that this is in fact a line bundle, and I can work with this more easily. All right, good. And the connection with the previous discussion is that this FDM, if there is something we know about it, is that it lands in here by the Néron mapping property. So it's a pullback of a Néron differential. The Néron differential lives on the smooth locus of the Néron model of my elliptic curve. So by the Néron mapping property, the pullback has to extend to the smooth locus of the domain. Okay. So this FDM is in fact a non-zero section here. Good. So all I need to do is to show that every non-zero section is not too small. Okay. So here's how it goes. Maybe I can use this board here. Oh, there is the screen. Maybe I'll continue here. Good. So here's a theorem. Let epsilon be positive if the level is large enough with respect to my choice of epsilon, then for every non-zero integral modular form, okay, and I can choose any admissible factorization for this, okay. We have that minus logarithm of the non-normalized Peterson norm. So I'll write here gamma 0 dm. This is weight 2, of course, okay. Is less than 5 by 6 plus epsilon log n plus 1 over 2 log n. So what this is saying is exactly what we needed, that these norms are not too small. They are at worst reciprocal of power of n. And that still is good enough to get a polynomial bound for the quantity I want rather than exponential or anything worse, okay? And this is, again, not just for FDM coming from this particular setting. It's in fact for every non-zero integral modular form in the sense of integral models, okay? All right, so here's actually when one has to work. So let me give an outline of the argument. So idea. So first, It turns out that this Peterson norm is too analytic. This is an L2 norm. It's just too analytic for the arithmetic computations we're doing. So one first compares this to something that's closer to arithmetic. So prove that the infinity norm, the supremum norm, is less than constant times the L2 norm. Okay, I'm writing a 2 not for way 2, but rather for L2, which is what's used to define the Peterson norm. Okay, so this norm is exactly this one, just for notation. Okay, so one has to prove a comparison and mind the fact that this constant is supposed to be uniform. It doesn't really depend on the level or anything. Okay, so how do we do this? So this is in fact boiling down to lower bounds for injectivity radius of Shimura curves, which in turn, well, over the complex, okay? This boils down to certain progress on Lemmer's conjecture. Okay. I don't need Lemmer's conjecture. I need some very special cases that are already proved. This is about how small the Mahler measure can be. Okay. So in fact, this looks analytic, but the input is purely arithmetic. All right, good. So now I need to show that an infinity norm is not too small. So how you show that the supremum of a function is not too small? Well, you find the value of the function where it's not too small. Or you can find a bunch of values where the average is not too small. And that's exactly what we do. At least here's the criterion. So 2. If a P algebraic point is conveniently located, then one can show that the height, the Arakelov height of this point is larger than minus logarithm of the infinity norm of G. And one has to show something because I didn't tell you what conveniently located means, okay? But it means where it lies at the level of complex points and how the section extends to the integral model. Okay, so for instance, you want the section to extend the multisection to extend in the smooth locus of the integral model. That's one of the conditions. And what is this thing? This is some stacky version of hyperbolic Hodge bundle. Okay, so when you go to the stacky version of everything, you do have a universal family, so you do have a Hodge bundle. And when I say hyperbolic, it means that the metrics I want to put on this line sheaf are coming from a hyperbolic geometry rather than Arakelov geometry. So it's not the usual admissible Arakelov metrics. It's the one coming from the complex uniformization. Okay. So one has this, and good, that at least is a criterion to show that this norm is not too small. Everything I need to do now is to find points that are conveniently located in whatever sense this is defined, and secondly, that the Arakelov height of those points is not too big. It's controlled, okay? So, all right. So here's how you go about that. Maybe I can use this board. I'll just move it up later, okay? So 3, you take P, a Higner point. Okay, so the good thing about Higner points is that just by imposing congruence conditions on the number field K, the quadratic imaginary field K, you can achieve that these points intersect the special fibers of your integral model anywhere you want. So you can control this conveniently located condition, at least arithmetically. Now, analytically, you'd like that this point avoids certain zeros of a modular form, and that can be also achieved, provided that the Galois orbit is large enough, by trivial reasons, okay? So, all right, so we need to show that you can find Higner points that are conveniently located. That sounds easy. The issue is that at the same time, the height cannot be too big. The good thing about these Higner points is that we know the height, okay? So when m is equal to 1, and that's important because then we have to generalize this condition, we really need to work with general m. So when m is 1, at least, one has the formula coming from Kolm's conjecture, and in this case it was proved by Kudla, Rappaport, and Yang, and then later by Yuan and Zhang. The height in the sense of Arakelov geometry, okay, is equal to a logarithmic derivative at 1 for the Dirichlet character attached to the number field, the quadratic field, plus a certain contribution which is really well understood. You put here the discriminant of your auxiliary field, and then the discriminant of the quaternion algebra, and then there is a constant if I want this formula to be correct. So Euler's constant plus log 2 pi. Okay, good. And all right, so it seems that everything I need to do is to show that I can choose my Higner point coming from a number field whose discriminant is not too big, is well located, okay, that's some sieve theory from analytic number theory, but in addition, I want this L function contribution not to be too big. It turns out that actually that's more or less asking for the non-existence of single zeros and more. Okay, if we have the Riemann hypothesis, that's fine, but otherwise we need to do something. And that something is coming from zero density estimates for L functions, okay? In this case, it's coming from work of Heath-Brown. So let me just say analytic number theory. So there exists PK, that's good, okay? So that will do it. All right, so that's a sketch of the argument, how it goes. And now I think I still have like 3 minutes, so I'm going to explain. I'm going to explain what's going on in the totally real case.
Can I ask a question?
Yes.
Well, so you define this integral model for the Shimura. And so you can use it actually to make the estimate for the no. Why doesn't this work for the usual modular curve? I mean, you could consider also the integral model and try to do what you have done.
Okay.
And why doesn't it work? You could bypass the Manin constant.
But the Manin constant is an integer. So when it comes to lower bounds,
yes.
When it comes to lower bounds, it doesn't really matter. So here's the thing. If you want to do something like this in the classical case, you can just take the Fourier expansion normalization. That gives you a lower bound for the norm, actually gives you an asymptotic formula for the norm. And then you want to compare the integral structure coming from Fourier expansion with the integral structure coming from integral model. That comparison was done by Edixhoven and later by, yeah.
I understand, but why what you have done here for Shimura doesn't work directly for classical modular curves?
Well, it does.
It does. So you get an inequality which does not involve the Manin constant. Then.
But the usual inequality you get doesn't involve the Manin constant either. Because think about this. If you don't define the Manin constant and you just take whatever the pullback is giving you,
yes.
It's going to be the lower bound you have for the normalized one times the Manin constant. But the Manin constant is an integer.
Yes.
And we're talking about the lower bound.
Okay.
Therefore, what you're asking follows from what we have. Okay? So the inequality points in the correct direction in that case. So what's interesting here is that in the classical, yeah, maybe that's the point of confusion. In the classical modular approach that's somehow better known, you deal with lower bounds. Oh, 1 minute, or is that a minus 1 minute? No. Okay. So in the classical, so maybe I will skip the totally real case for the benefit of making this more understandable. So in the classical modular approach, you deal with lower bounds for the Manin constant and the lower bounds for the Fourier normalized classical modular form, right? Now, in this approach, however, the norm of the classical modular form shows up in the numerator. So you want upper bounds instead for the Manin constant, and upper bounds for the Fourier expansion normalized modular form. The modular form part is fine, but then you have to deal with the Manin constant. So that's why it looks like in the classical case we need to do more work. The reason is that the non-classical case shows up in the denominator, so we need a lower bound rather than an upper bound. In this case, okay. All right, so I'll stop here better. Okay, thanks.
So there's still time for questions, and we need to use a microphone.
So I have more questions. So if we go back to your, I think, first theorem.
Okay.
Of course, one thinks about, there are so many consequences that one can derive from the ABC conjecture. So I'm thinking about what sort of consequence do you have from your weaker statement. In particular, I recall that there is this theorem of Elki's which says that ABC implies more than.
Right, okay.
So is there some sort of self-improving thing in your statement as well?
Right. So yeah, that's a good question. So just to have everyone on the same page, when you have the classical ABC conjecture, depending on what version you're using, you have many consequences. So in particular, the one about Elki's work showing ABC implies more del, it's not enough to have the version I stated at the beginning of the lecture. That ABC conjecture will not do it. You need the 1 plus epsilon in the exponent. So that already answers the question. When it comes to Elki's proof, already the version that I stated before is not enough, which is way stronger than anything we have. All right, so maybe a better way to answer that question is if you compare this with what comes from linear forms in logarithms, which is a theorem rather than a conjecture. How much improvement you get? Well, first, consequences you can get from linear forms in logarithms by means of this expression in terms of the ABC conjecture, you get the same consequences. So you recover all of that. In addition, there are other consequences that involve product of these valuations that are not accessible from linear forms in logarithms, like the one I explained involving the Tamagawa factors. Also, for instance, if you have questions about the number of divisors of an ABC triple, that also is something that you cannot approach using linear forms in logarithms, and you can do in this way. And there is also the hypothetical situation in which you have an ABC triple. I say hypothetical because we don't expect ABC triples to have exponents that are too big if we believe in the ABC conjecture. But since we don't have the ABC conjecture, if you take an ABC triple and you suppose that exponents are rather large and more or less of the same size, not necessarily perfect powers, but exponents of more or less the same size, you will get certain estimates coming from linear forms in logarithms, but then you get those estimates with certain roots, okay? You can save a whole lot in powers if you use this kind of bounds instead. So the answer is the consequences you get from this are whatever you have from linear forms in logs plus additional stuff. Yep.
So are there any further questions?
Maybe I can mention one more thing because I totally forgot to give credit to other people also. So there is also some previous work by Ram Murthy and myself using the classical modular approach to give bounds for Szpiro's conjecture that are exponential. Now those bounds are effective. So linear forms in logarithms will also give you something like this, but the constants are better, and this has been used recently by von Kannel and Matschke giving algorithms for finding solutions of S-unit equations and model equations. And that recent work is very interesting in case you want to see it. Yep.
So maybe one final question for your first theorem. The constant, maybe you said it, is it effective in terms of epsilon?
Yes. So what's going on there is that in full generality, the constant will depend on an application of Falting's theorem on certain modular curves. However, when it comes to the application to Frey curves, which is what you need for the ABC conjecture, what's really going on, why you need to apply Falting's theorem on certain modular curves, is because you want to have certain results in terms of a Serre's open image conjecture. But in the case of the two-adic representations, the two-adic images, that's been worked out. So you don't need to rely on Falken's theorem. You can just use the explicit results that are already available for the two-adic image. So for Frey curves, it is effective. In general, that constant will depend on some applications of Falken's theorem.
Okay, thank you. Final questions? So if not, let's thank Héctor again.